Hello and welcome to my talk today about fuzzing closed source applications. My name is René Freingruber. I'm working at SecConsult since about 5 years, mainly in the fields of reversing, exploiting and fuzzing. I'm also the trainer there for these fields. I also spoke at various conferences about topics like bypassing NMAT or application whitelisting, or how you can hack a company via firewalls and so on. And there's also my Twitter account if you want to follow me for reverse engineering and fuzzing content. A short word about our company. We were founded 2002 in Vienna, but we now have offices all around the world, and it's a team of over 70 security experts, so really technical persons. We conduct more than 400 security audits per year, and so it's also very important, we are currently hiring, so if you're searching for a job in the infosec field, just come to us. Let's start with the real topic, fuzzing. So the main idea of fuzzing is that you're starting an application many times, very fast, and we are always passing invalid, unexpected or some strange input, and we want to trigger some strange behavior or some vulnerabilities inside the application, and then we monitor the program to identify these vulnerabilities or bugs. And if you think about this, how can we generate this input for this application? There's maybe you can just give it some random data, but of course it's not very efficient. Another idea is that we implement a file format and protocol ourselves. For example, I'm implementing MP4 or PDF or AV or I don't know, some other format myself, but the problem is this approach is that this is very time consuming, and your fuzzer will only work for one specific protocol or file format, and if you want to fuzz some other application, you have to do the same stuff again and again, and this is very time consuming, and you also have the problem of the human error, so maybe you're just forgetting some stuff, or maybe you're thinking the same way as the programmer thought. And to deal with the second problem, we have this feedback-based fuzzing. That means we want to get some feedback back from the application. It means I want to execute the application and get back what code was executed in the application. For example, if I enter here a command, I want this orange marked part to be returned from the application. That means my fuzzer can now enter, for example, a command, and then notate this command. For example, you can add additional commands afterwards, like you can say command and then 1, 2, 3, 4. But this will reveal that we are still executing here the orange code, or we say command foobar and it's still the orange code. As soon as the fuzzer then replaces or adds the subcommand to it, we are starting, we are executing command and subcommand. That means the fuzzer will then get returned from the application as feedback, more code coverage. That means the fuzzer can then learn the file format itself, because now the fuzzer knows more code gets executed. That means he will put this input into the fuzzing queue and fuzz this input later too. And we then continue this, then the fuzzer will later fuzz this input and so on until it comes into the next if condition and so on. That means now your fuzzer can learn the file format itself and you don't have to implement it yourself. That means also you have to find some way to get this code coverage back from the application. And we can do this with several methods. The simplest one is we can just instrument the binary during compilation. EFL, American Fuzzy Lab, is for example doing this. It's one of the most famous fuzzers currently available, developed by Michael Zalewski, and it's implementing exactly this strategy. And the reason why it's so famous and used by so many people is that it's really simple to use. So basically you can start fuzzing in 1 or 2 minutes, and it's a really good design. That means it's really fast and has very good heuristics and finds many vulnerabilities. And the strategy is exactly the same. You just start with some input files, and then the fuzzer, every time it gets more coverage, starts to fuzz this input later too. That means the fuzzer identifies the file format itself. And there are of course many forks which I will come later on. Basically, you work with EFL by just compiling this EFL GCC instead, so the application works afterwards exactly the same, but it's now just instrumented, so a little bit slower. And the general idea is, if you look at the basic blocks, so this for example is the code from the previous program, it will just print test 1 here, test 1, or it prints test 2, and here's an if condition if you go left or right. And the basic idea is that the compiler is adding at all of these basic blocks additional code which says I executed this code. So if you just look at these 2 basic blocks here, test 1 and test 2. This is what EFL makes out of it. So we still have here the original code, like printing test 2 here, or we print here test 1. And yeah, EFL adds this code here. So EFL is now calling EFL maybe log. So we're logging that we executed this basic block, and EFL assigns statically random numbers to every basic block. That means in this case here, BE80 is now the value which identifies this basic block. The same way as 55DD identifies this basic block here. And since we are working here with registers, we have to store the old registers and restore them afterwards. And the first time I was saying that we are storing the code coverage, which is not really correct because we are storing edge coverage instead. So we are not storing, for example, we are not storing that we executed this basic block here. Instead, we are storing if we go this path here. So we make edge coverage instead. And the reason for this is because in fuzzing, you want to explore as many possible memory states as possible. And with edge coverage, you get more memory states. For example, if you have an if condition, there is no else part. Code coverage would always take this if conditional because more code gets executed. But if you take edge coverage on the other side, you will take one time the edge into the if condition and one time the edge skipping the if condition, the code incident. And that means, for example, your fuzzer can find cases where you do not initialize inside this if condition some code, which can also trigger some vulnerabilities. So it's important that we are using edge coverage. You see this here, this is the code which gets injected by EFL. So this is inside this EFL maybe log function. And you see here, because we're taking the current location, XOR the previous location, we're getting the edge out of it. And that means you can now distinguish these cases here. And we are also not just taking the previous location, the same value, we are shifting the current location to the right to get the previous location. That means we can now distinguish if you go from A to B or from B to A. So we now get a direction in those edges. So I now know if I go forward or backward. And also very important is saving everything here inside a bitmap. The reason for this is because EFL wants to very quickly check if we execute the application one time, we want to very quickly check if this execution resulted in more code coverage or more edge coverage. And you can do this by having this global bitmap with all the code which you now identified, which you previously identified, and then you get this bitmap back from the current execution, and then you just compare every byte, and if there is a mismatch, you have new code coverage. That's the reason why we are using here a bitmap. So this is called a Bloom filter. And we are storing not only that we executed an edge, we are storing here a hit count. So we are also storing how often we executed an edge, because with this we can identify if we executed a loop multiple of times. So the fuzzer can react on this also. And with traditional fuzzing, if you have here an input, the traditional fuzzing without feedback would just find vulnerabilities in this first stage here. And with EFL, with this feedback-based mechanism, you can find bugs in deeper levels, because EFL will identify if you mutate the input. This here, for example, would result in more code coverage, so it will start to fuzz this one too. Then it detects, okay, this also has more code coverage and goes then into deeper levels, so it goes into deeper if conditions to find bugs there. And that's why EFL is so efficient. If you start EFL, you end up with a screen like this. So I typically look here first, where you see the execution speed. So typically with EFL, you have the execution speed of several thousand times per second, which is really important. EFL must be very fast, else it's not really efficient. So at least you have to get 100 executions per second. If it's slower, you have some other problems. Later, you have several thousand times executions per second. And then the next look here at the right upper corner, where you see how many unique crashes we already identified and how much paths we already identified. So in this case, I'm fuzzing readlf, and since I have here 14,400 total paths, it means another 14,400 different ELF files which trigger different code in readlf. And this is also called corpus, these files. And I can use this corpus afterwards to fuzz some other applications. For example, I can use this 14,400 ELF files to fuzz afterwards a disassembler, debugger, IDA Pro, an antivirus engine, and so on. And the next thing we should look is here the runtimes. So you see this is running since 42 days, and the last new path was detected about 1 hour ago. And as long as you find new paths, you should continue fuzzing because the fuzzer can find new stuff. But if you find after 42 days still new paths, you maybe have some problems in your fuzzing, and you can then do something better, which will come later on. Here you can also see how much the bitmap is utilized. So as you see here before, we have here a modulo to bitmap size. That means we can have collisions inside this bitmap. That means if this bitmap utilization here goes too high, we can have too many collisions, and then fuzzing can also get bad. Then you should also, for example, increase the size of the bitmap. And the bitmap has also a size which fits into a L2 cache of the CPU so that the fuzzing is faster. And EFL also has this concept of favored paths. That means we are not randomly picking one of these 40,400 entries. Instead, we are picking this EFL detects with some heuristics that these 2,220 files are better to fuzz or to focus on. And these heuristics are really good implemented. There's some other fuzzes available like EFL fast or EFL fair fuzz or fuzzer, which try to make here better heuristics. But yeah, I would just take EFL or use one of them. So as already mentioned, EFL can learn the file format itself. So one possibility is that we just start fuzzing with a completely empty file. And then EFL finds the complete file format. But the problem with this approach is that it's very, very slow. So better approach is to download as many input files as possible before. So typically you can go to unit test pages or bug report pages to download sample files. Or you can just scroll the internet. You should change the DNS server every 6 hours or something like that, or you get blocked. So at the end, let's say you download 20 terabyte of PDF files. The next step is that you minimize these files. So, because it's very likely that two files will have the same code or edge coverage. That means the next step is that we are calling here this EFL Tmin, which will detect if two files have the same coverage, and then just picks the smaller file. So typically if you download 1 million PDF files or docx files, you can reduce them to about 3,000, 4,000 files with the same coverage. And then you just fuzz these 2,000 or 3,000 files instead. The next step afterwards is that we are reducing the file size with EFL Tmin. That means if a file is smaller, the likelihood that you trigger or flip or mutate the correct byte, which triggers the vulnerability, is much higher because the file size is smaller. Typically, or logically, it would make more sense if you call EFL Tmin first and afterwards Tmin, so that Tmin works with the reduced file size. But the problem is that EFL Tmin is very slow from the execution speed. So therefore, it's better to call Tmin first, after that Tmin, and after that I typically call Tmin once more because it's just a heuristic. So if you call it twice, it will further reduce the size of this input set because the problem is NP-hard. That's the reason why it's just a heuristic. And after that, we just start fuzzing. So just call EFL fuzz and pass here the program with the arguments, and it will do everything itself. So it's really easy to start fuzzing here. There's also a second fuzzer, which is very famous, which is called libfuzzer. But this fuzzer is only usable if you have source code and if you're developing with LLVM. If you're developing with LLVM, I highly recommend that you're using libfuzzer. Then I would highly recommend that you go to this tutorial here, which is really good. Because we're now talking about closed source applications, I don't want to go into details here. Another approach is that we just emulate the binary. So EFL ships with a mode where we can emulate the binaries QEMO. So you just have to pass the Q flag, and if you don't have source code, you can just emulate it, and it will just work. But I don't want to talk about this one today too much. Another idea is that you're just using the breakpoints. So I'm using a reverse engineering framework. You can use either Pro for it, or you use Miasm or Radar or something like that. And you then extract every address of every basic block in the application. And then you replace statically every first byte with a breakpoint. That means if I start up my application then, it will trigger many breakpoints. It means the startup will be very slow. But every time if you trigger this breakpoint, you can remove the breakpoint from the application. And also if you close the application, you have to statically remove the breakpoint afterwards. So this approach is very, very slow because we have a debugger, but it is useful in some situations. For example, if you download 20 terabyte of PDF files and you already have a very good corpus, so you already have removed these breakpoints from most of the files, you have native runtime. So if I'm downloading a normal PDF file and starting it up, it will not trigger any breakpoint because all of the normal breakpoints were already removed. But as soon as I find new code coverage, you will trigger one of these breakpoints and can then detect very fast that this is new code coverage with native runtime. And I think this idea is also very interesting because what you're doing with this is you're basically implementing code whitelisting yourself. So I can make, for example, the safest Adobe reader with this because I'm just whitelisting 2000 valid PDF files which just display text and images, and after that you can just display images with it. But you cannot do strange stuff like XFA or JavaScript or converting images and so on. I think this is also very often the case in fuzzing and protection mechanisms. They are very often related to each other. But the field on which I want to focus more today is about dynamic instrumentation frameworks. And that means the dynamic instrumentation frameworks can be used on closed source applications, and you can then add in front of the instructions or basic blocks your own code during runtime. For example, Tmin or Pin can be used for that. You typically get with these frameworks the tools like drun with Tmin or Pin with Pin. And you just call this application here, and after at the end you just pass the application which you want to execute, and with T you say what tool you want to execute. So in this case I want to execute a default tool shipped with the MRIO, which is called drcuff, which just extracts the code coverage. That means you can just download this dynamic instrumentation framework, call it like this, and you immediately get the code coverage back. And this also works for bigger applications like Adobe Reader or browsers and so on. And it even works with modern games and nearly with everything. And the same applies for Pin. For example, this will count the number of instructions. And you can also write your own tools with this dynamic instrumentation frameworks. And if you write your own tools, you can register for different events. For example, I can say, call my function if a new basic block is found, or if a new instruction is found, if a module is loaded, if a thread is created, if the program is exited, and so on. And you can then add code at two different locations, at transformation time and at execution time. So, for example, in the MRIO, if you want to execute an application, and you want the first time to execute this basic block A here. That means the MRIO will kick in, take this basic block A, and move it into an internal code cache, and will now always execute A from this internal code cache, but this will completely be transparent for the application, so the application will not notice that this is happening. So that means the first time you can register for this event at transformation time, so this will be triggered one time for this basic block A. At that time you can then say, I want to further add here in front of A additional code. This will then be executed every time at execution time. So it means if you want to get the hit count, so how often is this code executed, you have to make this here at execution time. For example, if you're starting Adobe Reader and I'm starting it, I'm loading a PDF, I'm closing it, and then I'm starting Adobe Reader again, and I make this 25 times with a single CPU core on a virtual machine. Without instrumentation, I need about 30 or 40 seconds for this. And if you're now adding this basic block coverage, so it means no hit count, it means I can extract this information at transformation time. You get about double or 3 times longer the execution time. If you're now adding hit count to it, it even gets worse because we have here to execute it every time at execution time. And if you're using edge coverage, it's really slow because edge coverage requires that you inject many instructions there, because you need typically 2 registers for this and you have to restore them and so on. So that's also one of the reasons why many researchers mainly focus on just basic block coverage without the hit count, because it's faster and faster. There's also a second framework, as already mentioned, which is Pin. So the main difference for me is, so Pin is the older framework, so more people are using Pin, and Pin is also more reliable. But Dynamo is noticeably faster. So you really make a difference that Dynamo is really faster by starting up the application, which is good during fuzzing. But the problem is that in MRIO often don't work. For example, we fast N-case images months ago, and this is just not possible to start with an MRIO because of some bugs in it. But in Spin it's just working. Or if you try to start a computer game like Counter-Strike Go, it's just not working with an MRIO because it will then give many error messages. But with Spin you can really start a modern computer game, you can add instrumentation to it, and you can really play the game, and it's just working. And I'll come to WinEFL. So I was talking about EFL. EFL can be used on Linux, but if you want to do fuzzing on Windows, you can use WinEFL, which is a Windows fork for it. It was developed by Ivan Fladrik, and it has two different modes. The first one is with an MRIO, so that means you can use this mode without source code, so for closed source applications. And the second mode was later added, which is SysC, which you can use for if you have source code. So if you have source code, you should use the second mode. And you can also implement pin with it, I don't know, in 1 hour or something like that, which is really trivial. So on Linux, EFL is heavily using copy on write. So on Linux, you can fork a process very fast. So EFL is not starting the application again and again. Instead, EFL is starting the application one time and then forking the application. Because this is very fast. Because of this copy on write, that means you can fork, you can copy the process, but the pages will not be copied. As long as you're just reading the pages, they will not be copied. But as soon as one process is writing to one of the pages, you have to copy them. That's the reason why fork is really fast on Linux, and you typically get a speed gain of a factor of 10 or 20 with an EFL fork server. But the problem is on Windows we don't have this copy on write feature, and so what WinEFL is doing instead, it's not starting the application again and again. Instead, it's starting the application one time, you execute your target function, and at the end of this function, you just jump back to the start of the function and execute it again. This is called in-memory fuzzing. So, we're just iterating through the function again and again. And it's very important that the target function which you want to fuzz has to fulfill some properties. And you also have to tell WinEFL what function you want to fuzz. And it's really important that this function opens the input file, passes it, and closes it afterwards. Because one problem is, if WinEFL executes one iteration of this function, and the input file is not closed, WinEFL can't write to it, that means WinEFL will shut down the application, and then you just spawn the application every time again and again, and you don't get the benefit of in-memory fuzzing. So it's really important that it closes the input files afterwards, and that the application is not calling exit process. And for graphical user interface applications, in the frequently asked questions we can read that they must be reachable without user interaction. So if we want to fuzz an application which has graphical user interface, a graphical user interface like an application where you have to click on a button so that you reach your target functions, you have two possibilities. First of all, you can automate this process with a scripting language like Autoit. Or I think that the better approach is that you're using the MRIO or pin with this. So what you can do is, for example, you can write your own MRIO tool, which logs this code coverage. And the MRIO has this concept of nudges. So it means you can, from an external process, send a nudge, which means a message. You can send this message to your own tool, and then react on this. And you can send with this nudge, for example, the message that you want to disable the code coverage. So typically run this tool, log the code coverage, start the graphical user interface, and as soon as it's started up, I just send this nudge to disable this logging, and after that I can just extract one of the last addresses which were logged. This is one of the last addresses when the graphical user interface is loaded, and then I can just say into MRIO change the path to the target function. Then you can reach it without user interaction, which is the fastest solution. And you can get this address of the target function by just enabling the log link, clicking on the button, and then you have this address of this function. But I will come to other techniques a little bit later how you can get this address. This here would be this Autoit approach. So for everyone who doesn't know Autoit, it's a really cool scripting language where you can automate Windows graphical user interfaces. For example, I can just say start Notepad, I can say here write into Notepad, hello world, or you can make button clicks and so on, and change the size of the window and so on. But I'm typically using Untitled as a pop-up killer, so in fuzzing you often have this case that you get many error messages popping up, and this script here will just iterate through all open windows and check if the title is, for example, engine error, which is the case with Counter-Strike, and just clicking then always on the cancel button that the boxes are going away. If you want to make this faster, so this is just a loop, so you always need a half a second to click this away. If you want to make it faster, you can use this code here from the third basic fuzzing framework. The one big problem with the dynamic instrumentation is that we're dynamically instrumenting the application. So if I start again 2 times, I have to instrument the application 2 times, which is bad in fuzzing, because in fuzzing I want to start the application as fast as possible, multiple times. So one idea is that we can make it statically with static instrumentation frameworks, which are, for example, EFL Tmin, so Tmin is the framework, EFL Tmin is the fork of it, or this sys mode. But the problem is that these frameworks are not so good developed like the MRI or PIN, and there's not so big community behind it. So typically we are now currently in this dynamic instrumentation field. And the last method could be that you're using hardware features, because with the hardware features we don't have to execute additional instructions, which means we are faster. For example, Intel PD, which is available since the 6th Intel core generation, for example, this laptop here has this Intel PD, can be used to get this code coverage information back. But the main problem is that you can just get this code coverage back and not more stuff like with dynamic instrumentation frameworks, which will come later. So in my opinion, there are 4 major fields which influence the fuzzing results on which you can work. I don't have time to talk about all of these fields today, but let's just focus on the most important ones. So fuzzer speed. If you can execute a fuzzer faster, you can process more test cases in the same time. That means you get better results. And there are several techniques which you can use to get to make the fuzzer faster. As already explained, you have this fork server implemented by EFL. We also have this concept of deferred forks. That means you can say that the fork is not happening at the main function. You can fork in front of the target function which you want to fuzz. That means you are skipping the initialization code. Then EFL also implements this in-memory fuzzing with persistent mode. Basically, libfuzzer implemented this in-memory fuzzing, and after that EFL also implemented it via the persistent mode. But the problem with EFL in-memory fuzzing is that it's not 100% in-memory fuzzing, because you still have the EFL fuzzer and the target application which you want to fuzz. You're not starting the application again and again, but you still have these 2 processes. That means process switches have to occur between the 2, which slow down the fuzzing process, and EFL is modifying the files on disk and not inside the memory of the application, which is also slow. Which, for example, libfuzzer is doing better. And you can then, for example, also use a run disk, or you can even remove API codes, slow API codes, or you can even go so far that you're executing Windows applications on Linux so that they're executing faster, and so on. So there are many techniques what you can do there. But as already mentioned, graphical user interface automation is also one problem. This is now just one example. So just that you can think about it. If you, let's say we want to fuzz MD5, which is not really a good target because MD5 is very simple, but let's just assume that you want to fuzz MD5, and if you would now have to, if you want to fuzz this application, you have to enter here some data, and then select here MD5, and then click on the calculate button. Jump back here, enter the next data, click on calculate, and so on. So if you automate here the graphical user interface, what do you think, how much executions per second do I get with this? So it's not really fast. And if you're on the other side, if you think about how many MD5 hashes you can calculate on a modern CPU per second, it's a much bigger number. So for example, I tested it, I was up to it, I was able to make about 3 executions per second, maybe a little bit less. But if you automate it with a debugger, so that you're fuzzing inside with a debugger, you get 705 executions, so it's much faster if you're doing in-memory fuzzing. But There's one big problem with a debugger, because debuggers are very slow if they write to another process and you still have this process switches occurring. If you implement the same as in MRIO, you can get up to 200,000 executions of this function, so that it's a completely other number than these 3 executions. So that's the reason why you should really do in-memory fuzzing. And I think we should also, within AFL or something like that, should also change to make real in-memory fuzzing, that it's really fast. And one big question is also, how do we find this target function which we want to fuzz? Because if you have source code, it's trivial, because you can just look up in the source code. But if it's a closed source application, it becomes harder. So there are several techniques what you can do. A really nice technique is that we can just use this dynamic instrumentation frameworks. So I'm executing the application 2 times. So let's say we want to find here the MD5 implementation of this program. So I'm starting the application 1 time while I'm covering the code coverage, and then I'm calculating the MD5 hash of some input. Then I close the application and start it again a 2nd time, and then I select some other hash and click on calculate, so I don't calculate MD5. And after that I can just subtract the first trace minus the 2nd trace, and that means everything which remains there will be the MD5 implementation of it. And you can also do this by looking up what functions will be executed in this A minus B, what functions will be executed 100%, which will be in the MD5 functions, and what functions will just be executed 3 or 4%, which will be very likely the functions which decide if you go to MD4 or MD5. And you can, for example, use IDPro Lighthouse plugin for this, to make this subtraction, or you can write your own Python script for this. And another technique is that we can just use this dynamic instrumentation framework to log all calls and all returns, and at every call and return I'm extracting what registers, the register values and the stack and so on. That means after that I get a very big log file, and I can then search inside this log file for a function which receives my input and which returns the MD5 hash. This way you can also find functions. This way you can also find, for example, malloc implementation of custom heap implementations. The old method is that you can just place a memory breakpoint on the input, and the first time that it is triggered, it's the target function. And we can also use a tape engine, which I will talk later on. The next area on which you can make a fuzzing results better is the input file size. As already mentioned, it's really important that your input file is really small, because smaller files will be faster processed, and it's much the likelihood is much higher that you find the correct byte during fuzzing. And I already mentioned 2 scripts here, which is Tmin and Tmin. Tmin can reduce the file size, but this is using a fuzzy approach. So it's basically just saying, I remove 1 byte, start the application, and check if it's still with the same code coverage. And then it's making it binary search, so it's a better heuristic, but that's the main idea of it. But it has some problems here. For example, 2 months ago I was fuzzing Mimicuts. I think most people here know Mimicuts, which is a very famous hacker tool, and it can work on memory dumps. Memory dump files are typically very big, so in my case it was 25 megabyte. If you start fuzzing with EFL on a 25 megabyte file, you will not find any results, because it's just too big. EFL will also not start with a file bigger than 1 megabyte, because it's just useless. So what I did is, I just executed Mimicuts and logged which bytes Mimicuts is really reading inside this memory dump file. And then I saw Mimicuts is just working with 2,200 bytes of this memory dump file. That means I just had to fuzz this 2,200 bytes. And then this means the file size is now 12,000 times smaller. That means my fuzz is now 12,000 times faster, because EFL is doing deterministic fuzzing. Which really brings a lot. So for example, with the forksor you get a speed gain of 10 or 20, but if you're reducing the file size, in this extreme case, you can be 12,000 times faster. So for example, this is a visualization of this input file. You see here 1,000 bytes printed, and the next line 1,000 bytes, and so on. At the left bottom is the header of the file, and every black byte is not touched by Mimicuts, and the red and yellow and white bytes that the brighter it gets, the more hit counts occur from mimicuts. And we can also, for example, zoom in here to the left bottom, and then we see here, for example, this is the header of the memory dump file. Here is the paging directory to find the stuff inside this memory dump file, which is accessed very frequently, which you see here because it's white and yellow. And yeah, and then just then run a WinDFL against this 2200 byte file, and then you can find many vulnerabilities. If you want to read more about this, you can just go to my blog here, and you can of course also find an exploitable vulnerability which is still not patched, I think. And yeah, I was using a debugger script for this. As already mentioned, debugger scripts are not really efficient. That means this script had a runtime of about 30 minutes, which I don't care because I just have to execute it one time. But a better approach is that we're using these dynamic instrumentation frameworks. That means with these dynamic instrumentation frameworks, I can add in front of every instruction code, in front of all instructions which move memory around, can add code to follow these moves. For example, if I move from one memory location to a register, and from the register to a memory location, I can follow this with a taint engine. There are some taint engines available, like libdft, which is a pin tool, which is not really fast, but I think it's the best currently available. There's also Triton and Panda and so on, but they are all not really designed for fuzzing. They are all very slow and don't work with very big applications. So I wrote my own script with the Memorio and this pin. It's much faster and more useful for fuzzing. I think I will release it in some months publicly. And these tools, you can do really cool stuff. So what I can do is, as already explained, I can log every call of the application. That means I can make a call graph here. So it's really a time-based call graph because you see here function 1 is called, function 2, 3, 4, then function 1 is called again, and so on. So it's time-based. And this calls some other functions. And then I have my taint engine. So the taint engine, when I'm loading the input file, I'm tainting the input. And then I just follow the taint status around the memory. So every time I move my bytes around, I taint this memory too, and I store at this memory address also on which byte it depends from the offset. So that I now know the memory at byte 2000 depend on the file on the input byte from offset 10 and 20. And that means I can now extract which instructions work with my input. And then I can extract, for example, this information. And as soon as I get this information here, I now know that the target function which I want to fuzz is, for example, this function, because this is the parent function of all the functions which work. And this is also working with closed source applications. And you can do lots of other stuff with it. For example, if you have an input file which is 5 byte big, so if you have 5 bytes here, and you know your fuzzer can make 100 iterations, 100 mutations. That means I can make 20, the old fuzzers would just make 20 mutations per input byte. But with my taint engine, I can extract which instructions work with which byte. So that then I know, for example, that byte 1 is read by 2 instructions. Byte 5 on the other side is not read by any instruction. That means we don't have to fuzz byte 5 at all, because it's not read, so it cannot trigger vulnerability. On the other side, byte 2 is read very often by 5 instruction. That means we want to fuzz this by 2 more often. And you can then add more logic to it. For example, I can say x2 is accessing the bytes 1, 2, 3, 4, so many bytes. That means it's very likely a copy function or a search function or stuff like that. That means you maybe don't want to count these hit counts here because it's just accessing all of the bytes. That means I don't want to fuzz byte 4 maybe at all, or I want to shift it very late so that I'm fuzzing it very late. And you can do lots of other stuff with this. For example, if I have this basic block here, which can go right or which can go left. So if I have an if condition, so right would take the if condition, left would say go to the else part. And with all of my input files, so every file in my corpus will always go the right way. But what I want to do is I want to go the left way, because I want to execute more code to find vulnerabilities in this left part. And what you can then do is you can search for all of these situations, and where you can influence the decision if you go right or go left. Because you have this taint engine, you know on which bytes this decision depends, and then just focus to fuzz these bytes to find more vulnerabilities. And you can do lots of other stuff with this. Like I already mentioned, you can automatically detect the target function which you want to fuzz. Then, in the closed source application, then I can execute one iteration of this function and use this state engine to see on which bytes this iteration is writing, on which global bytes. And then I know which bytes, which memory regions I have to revert to jump back to the start of the function, to start with a fresh memory layout, so that I have the same global variables in every iteration. The same I can do with, I can replace the heap management, and then I can just free everything which was allocated inside one iteration, so that I'm not spraying the memory, so that I'm not filling up the memory. Another very interesting idea is that you can just enable the hit count logging of the state engine for new code coverage. That means I'm downloading many PDF files, and then I find one PDF file which executes more code. Then I have the state engine enabled, and I just extract the hit count out of the new code which gets executed. That means what I get in return are the bytes which make this PDF file special. And then I focus my fuzzing on fuzzing these bytes, which will reduce the file size a lot and makes it fuzzing faster. But you should also fuzz the other bytes because of the cross effects. The next thing what you can do, as already mentioned, you can make this call instruction logging. That means you can use this technique to very quickly find heap and free, also malloc and free functions. So, for example, if you have a custom heap implementation, if you want to change it to your own heap implementation, you can also use this technique to find checksum functions. So if there's a checksum in the closed source application, I can execute one time my good input, get my log out of it, and then I modify some bytes. That means the checksum will be different. I execute it again, and I can then detect what functions now return a different value. And after that, the call graph changes, and then I can detect which functions are very likely checksum functions, and I can just disable automatically these checksum functions for my fuzzing. And you can do the same for error handling functions, compare functions, and so on. And of course, you can focus your fuzzing for promising bytes. You can also do a lot with the mutators, that you just use mutators which will find new test cases or which are special for your application. But I don't want to talk about this today. The last area is the detection rate. That means there are many cases where you maybe trigger vulnerability, but the application is just not crashing. For example, Heartbleed is a read-based buffer overflow which is not crashing. Or if you have here a heap overflow, if you don't work with the heap data too, you will not detect that there's a heap overflow happening. And what you can do is you can replace the heap manager so that every allocation is now happening at the end of the page. After that, you allocate the second page after it, which is not readable, not writable. That means if I'm now overflowing it, it will immediately crash the application. And if I'm underflowing it, I can use here some special patterns. That means this will immediately crash the application. And what you also can do is, if you free this data, and you have a use of the free part so that the application is working with the free data, it's typically not crashing. But what you can do is, you can just say, every time I free the data here, I just say this is also not readable and writable, so that means if there are accessing happening, you immediately crash the process. And of course, if you're doing now in-memory fuzzing, you have to track between the iterations or the allocations and really remove these pages afterwards, and so you will fill up the memory very quickly. For Linux you have this lib dislocator which is shipped with AFL. Windows you have page with application verifier, but I recommend that you write your own heap allocator because you can do additional stuff there. For example, one big problem is in the use of the free bug you allocate memory, you free it, and after that you just use it, the use step. And if you don't trigger this use step, you will not find the vulnerability because the use step will trigger the crash. And what you can do is, at every free, you can search the full memory locations if there's still a dangling pointer to this memory location, which is basically the same concept as Edge is implementing this memgc protection things. And of course, you just have to do this for every file in your corpus and not during every iteration. That's why it's still fast. There are also sanitizers which you can use if you have source code available. but yeah, if you're developing, you should really use address sanitizer, memory sanitizer, and so on. But the problem is that these sanitizers are very slow. For example, if you have an execution speed of 1,200 executions per second, with address sanitizer you just have 200 executions per second. That means what I'm typically doing is I'm just using lib dislocator or my own heap implementation for fuzzing. Then I'm fuzzing for 1 to 3 weeks, and after that the corpus which was generated by the fuzzer, you then give this corpus 1 more week with address sanitizer and so on. And you typically use memory sanitizer. If you have 1 core for memory sanitizer, 1 for thread sanitizer, 1 for undefined behavior sanitizers, you use 5 cores for address sanitizer, because address sanitizer is better to use. And yeah, here's just an overview about the different stuff. And this is the last sentence. It's very important that you understand that with fuzzing you can find bugs, but if you don't find bugs with fuzzing, it doesn't prove that your application is doesn't have bugs in it. And thank you for your attention.